Hey, I'm JP from FizzBee. I'm the founder of FizzBee. I'm just reading about SlateDB, and I wanted to model at least some parts of it using a formal verification tool that I built called FizzBee. So here, SlateDB is uh, it's an embeddable database like RocksDB or SQLite, but it's a key value store, and it uses an object storage as the backing provider. So you can use it on S3 or Blob Store or anything else, depending on the cloud vendor you use. I'm not going to do it full model the entire system, but only this this specific part. So as a key value store, it has only two operations, put and get. And when a put happens, it first writes to the write ahead log. Okay, on get, by default, it would read from the in-memory table, and if it is you set read level as uncommitted, it can actually read through write ahead logs as well. So when you put, first it writes to the write ahead log, and there is a periodic timer that moves the data from the write ahead log to an immutable val structure. So basically it's frozen, and then the frozen data would be dumped into the object storage, and once that succeeds, the content, the data from the immutable val would be updated to the key value store on an in-memory data structure. Then there are other steps which I'm not going to model for now, only this part. Okay. And yeah, here is a little bit more detail on the sequence of operations. So so this is a code on. I'll go. So as a model, we are going to just model it with using only two keys and two values, K0, K1 and V0, V1 for values, and we'll be supporting the two read levels, committed and uncommitted. The roles represent the various microservices or data structures. Basically, they are the components of the system. So here there are two components: the database itself, or a writer or whatever role, and another one is an object store. So the init action is the entry point for the model checker. So it initializes the state variables. So we have two. One of them the DB itself, or and the object store. Okay, here I'm defining an object store role as it just has one state variable, which is a dictionary, just a plain key value store. And on the role, the SlateDB, which is the bulk, you know, as you see, there are like these three: write ahead log and immutable val, and then a mem table. So I'm defining those. Val, again, it's a sequence. It's a sequence of tuples, the key and value, but yeah, it's a sequence. Same thing with immutable val, it's again a sequence. Whereas mem table, optimized for read, it's a dictionary of a key and value. Okay. And the index is more like for this like naming the write ahead logs. Whenever we process, we have to increment it. I think by design it is supposed to read from the list the persisted vals from the object store, but for now I'm just keeping it in memory. So since there are two operations, let me first before I go into what the action means, let's look at the put action. Method. Put just simply appends to the write ahead log with the tuple which has two elements, key and a value. As you saw, it's a tuple or a list, so it just appends to it. That's the only step that happens in the put. Okay. Second, the get option is a little later. We'll look at it. So and then so action is anything that like a function, but only thing is that the calling point is outside what we are modeling it. So someone else calls. We don't know who calls it, or we don't care who calls it. but it gets triggered. That's it's more like a request handler. Okay. So any is a way of choose any arbitrary value. So here it would eventually explore all possible values, but on each path it would choose one, which takes in from this particular list. Here it's again I'm choosing between all 4 combinations of these 2 pairs of key and values. Okay. And from that I'm calling the put function that we saw before. Okay. Once that put happens, again periodically there's another action, flush timer. Again, even though we call it timer, it's just another action. We are implementing the handler, and how it gets triggered is not part of the model. So it has a precondition. If the immutable write-ahead log is empty, only then it would proceed, and this one is just to prevent keeping repeatedly writing an empty write-ahead log. So the first step is it freezes the write-ahead log, then it flushes it to the object store. Third one step is updates the mem table, and then finally it clears the immutable write-ahead log. That way it can, the other later systems can continue to push to the immutable write-ahead log. Okay. So freeze val, all it does is it copies the write-ahead log into the immutable one, and then clears the other one. Similarly, flash, it just writes to the object store. Okay. And again, since I'm maintaining the index in here, I'm just incrementing it. Update mem table goes over all these the immutable write-ahead logs, and updates the dictionary or map, okay, with the key and value. So it's again pretty obvious. So these are the 4 steps. One thing also you notice is that there's atomic. There are like many actions which has atomic keyword, and flush timer doesn't have it, which basically means that after each of these steps, the side effects would be visible to other threads, and which also means that if the system could crash, or that particular thread of execution could crash. So yeah, that's what the being non-atomic means. Okay. Now for get, again the first step is choosing arbitrarily choosing any key, and again arbitrarily choosing a read level, either committed or uncommitted, and then I'm calling the get. So get function. The get function, if it is uncommitted, it is first looking at the write-ahead logs, both immutable and the immutable ones. If it is finding it, it returns from there. Otherwise, it looks at the dictionary, the mem table. So yeah, once you run it, in this case I have already run it, so I'm just opening it out. Okay, well, noticeably one thing you notice is that I don't have any assertions here. Ideally, as a model checker, we would want more assertions. We'll look at it later. For now, I'm just showing how the this part works, and the sequence diagram. So let's try with this put action, and you can see we can choose. This is the step where we are choosing any pair of key value store, right? So in this, when we are exploring this, let's say K0 K1, which means basically it chose that particular path. So on the right-hand log, it added the K0 and V0 in that list. And let's say after it added, let's say we trigger the flash timer. The first step is it is freezing it. So from right-hand log, it moves to the immutable right-hand log. And next is if we continue, so basically after this, it would flash to the object store. So yeah, it wrote to the object store. This is the write-ahead log, the 0 file, and it has a list of the tuples. Next step is copying to the mem table, and finally done. So basically it cleared the immutable val. So now let's write another one. So in the same K0 V1, so it was returned to the right-hand log. Okay, before we proceed, let's say call a get for the same key. Let's read the uncommitted level. You can see when it is reading uncommitted, it would have returned V1 because it is looking at val. and if we are doing it on committed only, it would return v0 because it's only looking at the mem table. So now you can also simulate, like, what happens when there are system crashes. In this particular case, technically it would deadlock. Since I am not testing it, you won't. I don't have the assertion. You probably won't notice. So what would happen is that let's say when the flush timer happened, so it copied to immutable val, and if, let's say, for some reason that thread crashed, boom, then again, technically it's not considered deadlock because things would move, but then the immutable from here, it would never recover. So the system will never write to object store again, okay, because we don't have those kind of handlers. So those have to be modeled in the model. I'll show that later.